Hello students, welcome to my lecture series on reinforced concrete structures. In this class, I am going to discuss about introduction to flanged beams. So, in previous classes, we have discussed about design and analysis of singly reinforced beams and doubly reinforced beams. And then we have discussed design and analysis of one-way slabs and two-way slabs. From today's class onwards, we will discuss about flanged beams. So before starting up this class, let me discuss what is the beam is. Beam is a horizontal structural member which is subjected to transverse loads. So this is a horizontal structure member. I will consider it as a beam and it is subjected to a transverse loads and which is supported over some support. Say here it is supported over some simply support. This is called as a beam, right? Other words, we can explain in other way also. Suppose this is the axis of the beam. It is a axis of a structural member. The load is acting perpendicular to this axis of the structural member. That also called it as a beam. And these beams are classified based on their support condition as well as their shapes. Based on support condition, we know that beams are simply supported beams and fixed beams. If the support at the end of the beam is fixed, then we can call it as a fixed beam. And if the simply supports are provided at the ends, we can call it a simply supported beam. And based on the shapes also, these beams are categorized into two categories. Based on what? Based on shape. Based on shape. So those are what? One is a rectangular beams, or here we have square beams also, right? And another type of beams are called a flanged beams. What type of beams? Flanged beams. Now what do you mean by flange? So any projection or appears you on the top of a beam at the both side or one side, that is called a flange. So let us discuss what is actually this flange beam meant by. So you know that in reinforced concrete constructions nowadays the slabs and beams are casted monolithically. What do you mean by monolithic? Right, slab as well as these beams are cast. Casting means a preparation of a member, means concreting the particular member. Here the concreting can be done for slab and beam or at the same time. So those type of constructions, RCC constructions, are called monolithically casted. So how it will be done? It will done for formwork for beams and slabs are erected together and a concreting operation can be done at the same time. The operation will be done from bottom of the beam to the top of the slab. Say, let us take an example here. Here I have, this is a beam, and this is a slab. Here if you see here figure, these two are casted at a same time. So I can call it as a monolithic construction. How it is casted? First we have a formwork in this shape. Then concreting will be done from bottom of this beam to the top of the beam. Right. And such constructions, a portion of a slab act integrally with the beam. So now if you do like this casting of a beam and slab at a time, then a portion of a slab, the slab will be act integrally with the beam. What happens then? If you apply any kind of load over the beam or that hold this monolithic structure, if the beam bends in this direction, slab also bend in this direction. The same thing we'll see here, a bent shape. As these two are a monolithic construction, the beam is bending in this fashion. The same fashion our slab also bends. This is called a T-beam action. What do you mean by T-beam action? if the beam bends, as well as slab also bends in the same direction, that is called a T-beam action. Right, as I told you, these slab and beam are integral each other. A slab is the integral part of a beam. How it will be made? Here if you see, the stirrup what we provided in the beam are extended into the slab. See, this is a stirrup which will be extended into the slab portion also. Right? So this made a integral connection between this slab and this beam. That's why we can call this slab is a integral part of a beam. So due to this portion, this slab will develop or will give you a extra concrete onto the beam in compression zone. Let us say you know that this is a neutral axis of a T-beam. Assume that this is acting here. Above the neutral axis, we have a compression zone. As we are providing a reinforcement here, so it is a tension zone. Right? Generally, the portion of beam in compression zone is like this is only. This depth will give the portion of beam in compression zone. But this additional concrete also there onto the beam, it is due to because of a flange provided above this beam. So this portion of a concrete will give additional compressive strength to the beam so that it will resist additional compressive stresses. Right? So these flange are occur due to projecting the slab on either side of the beam. So this is called a flange, this is a beam, and these two are casted monolithically. That's why a slab is an integral part of beam. Right. One more point here. The flange of the beam contributes in resisting what? Resisting compression by adding more area of the concrete in compression zone. So same thing we have already explained you here. And as a result of this increased or extra area of a concrete in compression zone, it will increase the moment of resistance of the beam. Right? As moment of resisting of beam, how it is increases? The concrete is very strong in compression, so we are providing more compressive forces to resist the compressive stresses, so that at the same time the momentic resisting capacity in compression zone also increases. So if the flange is located in tension zone and the area of the concrete area of the flange to be neglected, and then beam treated as a rectangular beam. How it is? Say this is your a flanged T-beam. Right? Say your neutral axis is somewhere here. So let properly down somewhere here. Okay? So neutral axis is here. Right? Now in this the concrete which is above the neutral axis, it is in compression, and the below the neutral axis it is tension. Generally in design of beams we will neglect the area of concrete provided below the neutral axis, then this will be treated as a beam. Right? As your neutral axis in the flange, so the total flange area will be considered as a beam, and the neutral below the neutral axis, the concrete what we are provided in the flange is neglected. That concrete is called as a cracked concrete, I can say, and will consider only the concrete provided above the neutral axis. Right? Right. Then type of flanged beams. What is the meaning of, what is the different types of flanged beams? The most commonly used flanged beams are two types. One is T-beams and L-beams. What are those? T-beams and L-beams. So what is the definition of T-beam? When the slab occurs on the both side of the beam, the section look like a T, and this is known as a T-beam. Right? Say it is a T section. Right? And if you draw the projection of this like this, so here like this, right, like this and like this, and see it is appears to you like a what? T. in section. So these types of beams are called T-beams. Okay, and another type of beams are called, see, T-beams. One more point regarding this. This is a rectangular portion of a T-beam, and this is a projection from the slab in one direction. It is a projection from the slab in another direction. So what is it? The slab occurs on the both sides of the beam. So this is a beam. Slab occur in this direction and in this direction also. Then we can call it as a T-beam or a flanged beam, that is in the shape of T-beam. Okay, so one more type of beam we have, that is L-beam, and the end beams are called the L-beams. These are provided generally around the staircase and lift openings which have the slab only in one side, and they are termed as a L-beam. Say here, if you take a staircase, so for a staircase we will provide a beams like this, right? And this is a beam, and remaining portion, this will be a landing slab. What is this portion? It is a landing slab, and this is a beam. See how we are provided. So the beam are provided at the end of this, what is that, at the corner of this landing slab. So these are in the shape of inverted L. So these are all called L-shaped beams. And not only they are provided in staircases, they are also provided in as a ring beam for your lift. As a ring beam for the lift. So say, so this is a lift hole, and this is the beam what we have provided on the top. So this is what your ring beam. So if you observe that, what is the shape of the beam at the corner up to here to here? So this is a L, and similarly here to here it is a L, and here to here it is a L. So always these L beams are provided at the corners or at the end of the beam. So I take here example of a continuous slab. So you know the continuous slab means it is supported over a many supports. So see here we have one end of the beam, and this is another end, it is a continuing end. And if you observe that this one middle one and this is middle one, and so I can call it as a intermediate ones. So what are those? Intermediate one, and this is a intermediate one, and this portion is a end one. At the ends, if you observe the beam shape, it is what shape it is? It is a L shape. And in intermediate state we have a T shape, alphabet T shape. So generally T shape for flanged beams are provided in intermediate portion of a beams or slabs, and at the ends will provide L shaped beams, right? So in L shape also this is called a flange, and in T beams this is called a flange. That's why these two are called a flanged beams, right? Now we'll discuss what are the different types of T-beams and what is the T-beam means. You know, already discussed that T-beam means the slabs are occur both the side of the beam. The section is called a T section, or the beam is called a T-beam. And these T-beams are classified based on the mode of casting. What is that? Based on the mode of casting, the T-beams are two types. How many types there? Two types. Those are called monolithic T-beams. What are those? Monolithic T-beams. And another one is monolithic T-beam. Another one is isolated T-beams. So what do you mean by monolithic T-beam and what do you mean by isolated T-beam? Here the monolithic T-beam means your original beam and the slab are casted at the same time, and now your slab, this is a slab is your integral part of this beam, right? And the stirrup what you provided for the beam are the stirrup what you provided for a beam are extending into the slab portion, so that they will become a single member, right? Here if the load applied onto this structure, if the beam bends, your slab also bends simultaneously with the beam. So these type of beams are called monolithic T-beams. So the definition given: such type of beams which constructed by molding the rectangular and slab together. What you did here? You are molding this rectangular beam and slab together, and it is looks like a a rectangular beam which is supporting the slab, and if you see the front view of that, it is appears in the shape of a alphabet called T, so that it is called a monolithic T beams. Similarly, we have isolated T beams, such type of beams in which flange and this flange and these beams are not connected, they are separated each other. Suppose this is a slab and this is a beam section, but in appearance they are looking like a T, but they are not having connection at their junctions. That's why it is a single one, it is also a single one. They are independently act together, but they are in section, they are appearing as a T. That's why they are isolated T beams. Moreover, they are not casted at the same time. Slab is casted at one time and beam is casted at another time. So they are not casted at another time, plus they are not having connection at their junction. That's why we can call it as a isolated T beams. Okay. Next, we have some notations for T beams, means components of T beams. So first we have actual width of the flange. What is that? This actual width of the flange, that is designated with a small b. It can be seen in this section of a T beam. So this is what your actual width of the beam. Okay, actual width of the beam. Then we have overall depth of the beam. So from extreme fiber of the this slab to the bottommost fiber of the beam, the distance between these two is called what? Overall depth. Then we have effective depth. You know the definition of effective depth of the beam, that is extreme fiber of the slab to the centroid of the tensile reinforcement. The distance what we have, that is called a effective depth of the beam, that is designated with a small d. And df, capital D suffix f, that is a depth of a flange. So this we can see here, this is a depth of the slab, and this is equals to your thickness of the slab, is equal to thickness of the slab, or I can say depth of slab. And BW is the width of the web or width of the web. This can be seen here. So this portion is called what? Width of the web, that is designated with a alphabet B suffix W. So there are some notation hereafter. When we design or analyzing the T beam, we'll use this notation for our coming steps or coming lectures. Say, let us discuss a one by one component of a T beam. First we'll discuss what is the actual width of the beam. The definition of actual width of the beam is, it is equal to the distance between middle points of the adjacent spans of the slab. So what is middle point of adjacent spans of the slab? Say this is a beam here, this is a beam, and this one up to here and this one up to here. Say this is L1 is one of the adjacent span to the beam, and the span of that beam is L1, and we have one more adjacent span in the right side, that is L2. Okay. Now what is this actual width of the beam means? It's a distance between center or middle points of two adjacent spans of the slab. So this is one adjacent slab, and this is second adjacent slab of a beam. So it's the center point here. So this is a middle point of the left hand span, and this is the middle point of the right hand span. Say here the span length is L1, the middle point of the span is say L1 by 2. What is that? L1 by 2. I am indicating with say some x1. Right? x1 is the middle point of the span, left hand span with respect to the web. Similarly, calculate what is the middle span length of right hand span, that is L2 by 2 is equal to x2. What is this? X2. 2. So what is the final total clear distance between middle points of adjacent span? So this x1 and this width of the web plus width of the middle point of the second span. So I can write the actual width of the flange or the beam is x1, this one, and x2, this one, and this width of the web BW will give me the what? Actual width of the beam or actual width of the T-beam. Similarly, another component we have is width of the web, that is designated with a BW. Right, width of the web is the width of the beam supporting the slab, right? So in a T-beam, say in a T-beam, so it is a T-beam, this is BW. Now what is doing? This width of the beam is supporting this slab. So the width of the beam which is supporting the width of the slab is called a width of the web. So I can call one more point regarding this is it should be sufficient enough. The width what we provided for a web is sufficient to what? Accommodate this tensile reinforcement. What is that? A tensile reinforcement. Tensile reinforcement, it has to be accommodate. Okay, and generally this width will be provided based on the ratio of overall depth of the web to the width of the web. Say the ratio provided is BW by, what is that BW? Your width of the web by a depth of the web must be varies the value or must be chosen the values between these values, that is 1/3 to the 2/3, right? And here example is a BW and this will be your a DW. The ratio of this to this must be varies between 1/3 to the 2/3. Like that we can provide a width of the web so that we can accommodate tensile reinforcement. Next one is thickness of the flange. This thickness of flange generally designated with a D suffix F, and this is equal to your thickness of a slab. What is that? Thickness of slab, I can write generally T suffix S. Okay, this is equal to thickness of slab. And overall depth of the beam is designated with a capital D. You know the overall depth is, again I will draw a T-beam here, just I will show here what is that overall depth. That is distance between topmost fiber to the bottommost fiber of the beam is called a overall depth of the beam. How to calculate this? This is what sometimes we can call it clat. Here we have tension reinforcement and a DF is equal to DF plus, and this is what your depth of web DW. So overall depth equal to D equal to what? This DF plus DW. DW is depth of web portion, will give me the overall depth, and is generally assumed for 112 to 115 in case of simply supported beam. For the span 112 to 115 in case of simply supported beam, right? Next we have very important topic, effective width of the flange. Generally this will be designated with a P suffix F. So what is the definition of effective width of the flange is? So it is very important with respect to design and analysis. It is the imaginary width of the flange over which the compressive stress is assumed to be uniform to give the same compressive stress along the effective width of the flange. What do you mean by this? So if you see the compressive stress distribution for total width or actual width of the beam and effective width of the beam, see if the actual width of the beam, it is a theoretical one and it will varies like this. So at the topmost and bottommost fibers is somewhat less. At the web region it is a more, right? And see, if you see that your B and BF values from this figure, your B is greater than BF. B is actual width of the slab, actual width of the flange, and BF is effective width of the flange. Why it is lesser? So for that I will give example here. So let us consider a T-beam again. This is a T-beam, right? And if you apply a UDL over this or any kind of loading, the definition of effective width is on how much width of a flange of a T-beam will effective means it can able to resist the load, that width will be considered as a effective width of the flange. So because of load at the ends of the beam may not be have capability to resist the loads which are coming onto this may bend like this. So from this figure I can say the effective portion of the width is this one, right? So in which region in which width of the beam is effective to carrying the load, that width will be considered as a effective width of the flange BF. Though we have this total width is called what, from here to here it is called your actual width. See, your actual width is greater than BF, right? And similarly I will take one more real life example here, that is here. Take one more example here. You take the person, one person, say he is standing like this, and assume that this part is a web of the person and is expanding his hands like this, right? And say these are the palm of a person. For example, I am taking here. So if you apply a load here, here and here, he can bathe. If you apply a load here and here, he can bathe. And if you apply a load here at the wrist of him, he may not bear, at the wrist may bend like this because of this load, right? On which portion of length your hands are effective? From here to here, right? Not here to here, here to here. So this length or this width of the hands, I can say effective width. In this region my extended hands, length of the extended hands are effective in carrying the loads. In similar fashion we have defined the effective width for T-beam here. I hope you are understood here. And again, if you see the definition, it is an imaginary width. We cannot see practically what is that effective width in the structure is. That's why I can call it as imaginary. And if you see the stress distribution, over this width, your stress remains uniform. So wherever you measure the compressive forces are same along the effective width of the beam. That is the meaning of this effective width. Clear? Let us go to next point, the Codal provision for calculation of effective width of the flange. So according to the IS 456-2000, there is a clause 23.1.2. There are for monolithic beams to calculate effective width of the flange for T-beams, the formula is this. What is that? BF is equal to L0 by 6 plus BW plus 6 into DF. Similarly, for monolithic L-beams, BF is equal to L0 by 12 plus BW plus 3 into DF. And while giving this two equations for calculating effective flange width, there is one condition, or I can say note is given by IS 456-2000, that is that, but in no case greater than the width of the web plus half the sum of the clear distance to the adjacent beams on the either side. What do you mean by this? The calculated effective flange width by using this Codal provision are not more than the condition given here. What is this condition? This condition already we have explained you. Again I will explain here. That is a slab and beam system, right? So this is what your L1, slab in adjacent sides of the beam. This is L2. Say this is a beam, right? Over the beam we have a slab casted monolithically. What said? The value of effective flange width calculated, in no case it should not be greater than width of the web, that is width of the web, right? This is width of the web, okay, plus half the sum of the clear distances to the adjacent beams. So what is the clear distance of adjacent beams? This is one beam and this is one more beam. From this beam, this is L1 and this is L1. What is the half of this? So here we have half and here we have a half. So this is L1 by 2 plus L2 by 2, right? And whatever the value BF we have calculated from Codal provision should be less than this value. Okay, that is the meaning of this point. So this point I have explained in when we are calculating actual width of the beam, that is x1 plus x2. The x1 equal to L1 by 2 plus x2 equal to L2 by 2. Okay, so this is how we calculate the effective flange width in monolithic beams. Similarly, how to calculate the flange width for the isolated T-beams. Here also one condition given in your IS 456-2000, that is for isolated beams the effective flange width shall be obtained below. Below means the formula which were given below, but no case greater than the actual width of the beam. So actual width of the beam B is equal, what we calculated is equal to that your x1 BW, that is width of the flange, sorry, width of the web, plus x1 is the half the distance of clear span in adjacent left hand direction, adjacent span, and x2 is the half the distance from the beam of a right hand adjacent span. So the no case the value of effective flange width what we obtained from these formulas are greater than this value. So finally I can say our BF what we calculated, effective width of the flange, should be less than actual width of the beam, right? Then how to calculate this BF from the formula? BF equal to L0 by L0 plus B plus and plus 4 whole plus BW for isolated T beams. For isolated L beams the formula is like this. You know the BF is effective width of the flange and BW is width of the web and DF is thickness of flange, B is actual width of the flange. Here one more important term we have. What do you mean by this L0? Right? L0 means the distance between the points of zero bending moments in beams. So what do you mean by this? The meaning of this, here we have L0 in these isolated beams and here we have in monolithic beams also. So let me define clearly about this. So listen carefully here. So I will take a simply supported beam here. It is resting over a two simple supports like this. Okay, two simple supports like this, and the span of this beam is, say, or I can call it is a effective span is L, right? If you apply any kind of load on the simply supported beam, it will bend, or the bending moment diagram of this will be like this. If you observe at this end the bending moment is 0, here what? Your bending moment is 0, and at this also the bending moment is 0. So what is the L0? The distance between the 0 bending moment beams. So here a zero bending moment, and this is a zero bending moment on a beam. So the distance between these two is called a L naught. So this is how we calculate L naught value. I think you understand this. And this is for simply supported beam. And if you have a continuous beam, so our continuous slab, you have multiple supports, then the code is suggested for that for a continuous beam or S frames, L naught may be assumed as 0.7 times of effective span. Say, what do you mean by this? I will draw a continuous slab here, and the support is 1 here, 2 supports, 3 supports, and 4 supports. It is a span 1, span 2, and span 3. They are called effective spans. And if you want to calculate L naught for this, how many spans we have? We have a 3 spans, and as it is a continuous one, how much we have to take? 0.7 times their effective length. So 0. Into their effective length L. So this value will give me the L naught for continuous beams or slabs. So this is how we calculate L naught values for simply supported as well as continuous conditions, right? And we have a Codal provision for minimum reinforcement provided and maximum reinforcement provided for a T-beams. So as per IS 456-2000, the clause number 26.5.1, the minimum reinforcement should not be less than that given formula. That means the area of minimum reinforcement, that AS, should not be less than the value which we obtained from this condition. That is AS by BWD into 0.87 by Fy. Here AS is minimum area of tension reinforcement provided, and BW is a breadth of the web, and D is effective depth, and Y is a characteristic strength of the steel, or I can say yield strength of the steel, right? So the area what we obtained, the area of steel what we provided in the T-beams or the flanged T-beams, that should not be less than area of area we can calculate it from this formula, right? And then we have a provision for maximum reinforcement to be provided. The maximum reinforcement should not be exceed 0.04 BW into D, or I can say 4% of, what is that, 4% of gross cross-sectional area. 4% of gross cross-sectional area either is B into D. Right? We have to check after area of steel obtained from provided in the T-beam. Then we have to check for minimum area of reinforcement and maximum area of reinforcement. Should not exceed this value and should not be minimum that area. Right. So let us see the advantages of a T-beams. Here we have few advantages. As the slab is monolithic with the beam, it shares the compression force, hence it increases the moment of resistance of a beam. So as already discussed you, in T-beams, here beams and slabs are casted monolithically, right? Actual beam is up to here only, and along the length of the beam, longitudinal direction of the beam, we have provided this much extra thickness, of a concrete over the this beam. So as we are providing concrete in compression zone, so it will give the more compressive strength, so it will resist the more compressive stresses, hence it can increase the moment resisting capacity of a compression zone. So as we are providing this concrete in the flange region or the above the beam, so that we can reduce the depth of the actual beam, and as it has a more moment resisting capacity, so the maximum deflection occurs in this is less. So same point I have listed here, and that increase the moment resisting capacity, and the depth of the beam required is less, and maximum deflection are less. Clear? Right. So let us see some problems and how to calculate the effective flange width of a simply supported T-beams as a monolithic as well as isolated beams. So let us see the first problem. Find the effective flange width of a following simply supported T-beam. What type of beam given? It is a T-beam, and does not mention whether it is an isolated T-beam or a monolithic T-beam. Is not mentioned means it is generally monolithic T-beam, because an actual practical construction will use a monolithic T-beams only. Isolated T-beams are not practically possible. We can study theoretically only, right? So is not mentioned means we have to use it as a monolithic T-beam, right? For that, the effective span given is 5 meters, and center to center distance, the center to center distance of adjacent panels are 4 meters. So what do you mean by this? Say this is a panel given to you. Say this is a slab and beam system, right? Here. So this distance is given to you. The center to center distance of a panels. The center to center distance of a adjacent panel. Say from this here and here. So this distance is given 4 meters together. This total distance given is 4 meters together, and breadth of the web is 300 mm. Thickness of slab is 110 mm. Right? Based on that, we can write what is the given data is. So L is effective length is 5 meter. The BW is 300 mm, and thickness of slab given. As you know, the thickness of slab is equal to the depth of the flange. I can write so TS, right? And as you know that as we are calculating for simply supported beams effective flange width, and for that L0 we have to calculate. So L0 for simply supported beam would be calculated like this. As a simply supported beam is subjected to any kind of load, the bending moment will be like this, and the bending moment at this support are 0. You know the L0 is a distance between 0 bending moment points. Bending moment 0 here and 0 here. So bending moment 0 occurs at this support, and at this support, and the distance between support we have is L, and that distance between 0 bending moments also same. So L equal to L0. The same point will be given. Since the beam is simply supported, distance between the points of 0 bending moments L0 is equal to L equal to what? 5 meters. So let us proceed for next problem. Next problems steps. The clear span of the slab to left and right of the beam. So here I am to calculate what is the clear span from the left and right of the beam. So for this, again I will explain you here. As I told you what the center to center distance of adjacent panels. Here I will define you what is the clear span of the adjacent panels. Right. So here this we have to calculate now, and this we have to calculate in this direction. Right. This is the BW, and this is a x1 clear span from the your side of the beam web, and this is x2, right? So this one and this one we have to calculate, but given is center to center distance between these two. Okay, what we'll do, from total distance, if you deduct this value, then we'll get what is that, x1 plus x2. We have to calculate from this what is x1 and what is x2. Finally, what is x1 plus x2 is, right? X1 plus x2 we have to calculate. So center to center distance of adjacent panel is what? How much given? 4000 mm, and this is x1 and this is x2, and we know that center to center distance from here to here, it includes web of the beam also. If you deduct the web of the beam, then we'll get what is the x1 plus x2. There is a clear span of the slab to the left and right of the beam. So that is for center to center distance adjacent panel minus web of the beam will give me that value. The 4000 minus 300 is the width of the web. I will get finally that is 3700 mm is the clear span of the web to the left and right of the beam. So finally now we have to calculate effective width of the flange. The effective width of the flange should be least of the following. What is? One is from Codal provision we have to calculate, and another is that this distance what we obtained here. So let us calculate for the Codal provision. The Codal provision, as we have to calculate the effective width of the flange for whom? For the monolithic T-beams. For that BF equal to L0 by 6 plus BW plus 6 into DF. For that 5 by 6, L0 is 5 and 6 is given in the formula. BW is 300, width of the web 6 into DF is a 110. We'll get 1793.3. Then another condition is, that is BF. We know that, what is that BF? Effective width of the flange. We can calculate another way also, that is finally we can call it as a actual width of that is the distance between these two, center to center distance between these two, that is already given to you. So this is 300, this is x1, this is x1. Again add here BW plus x1 plus x2. So if you add together, we'll get, that is 300 is the BW, half of the 3700 by 2 is 1850, half of the another side 3700 is by 2 equal to 1850, we'll get 400 mm. So effective width will be provided is minimum of these two conditions. So the minimum value we got with respect to the Codal formula, that is 1793.333 mm. So let us discuss one more problem. That is, find the effective flange width of a following simply supported isolated T-beam. In previous case it is the monolithic T-beam. In this case it is a isolated T-beam. For this the inputs are effective span is 5 meter and actual width of the flange given 750 mm and width of the web is 230 mm, thickness of the web is 110 mm and width of the support is 230 mm. So from that we have to write the given data. Effective length of the beam is 5 meters and width of the web is, it is not a 300, sorry, it is a 230 mm. How much? It is a 230 mm. 230 mm, make it correct. And a DF, effective width, depth of the flange, or I can say thickness of flange, is equal to 110 mm and actual width of the flange is 750 mm. As you know, we are calculating effective width of the flange for simply supported case. You know, the simply supported case is like this, where the bending moment we get for the simply supported beams are at the support. So the L0 can be calculated, the distance between the zero bending moment points, so that is equal to L. So for this beam, L is equal to your L0, because we are getting effective length from the center to center distance between support, and the same time in the center of the support we are getting a zero bending moment for simply supported beam. The distance will be same. So since the beam is simply supported, the distance between the point of zero moments L0 equal to L, that equal to 5 meters. Now as given that isolated T-beams, the effective width of the flange is least of the following, that is from the Codal provision, another is actual width of the flange. So from the Codal provision you can calculate L0 by whole by L0 by B whole plus 4 whole plus BW. If you simplify that, if you substitute all those L0 and BW values, we will get the effective width of the flange with respect to the Codal equation, that is 698.88 mm, and the actual width of the flange is 750 mm. The minimum of these two is 698.88. So adapt flange width for isolated T-beam is 698.88 mm. So this is all about your today's lecture. Based on the today's lecture, we have some quiz questions. Let us discuss those also. What is the first question? The T-beam action is possible only when slab is cast first, beam is cast first, C, slab and beam are cast together, and none. The slab action, the beam action, T-beam action will occur when slab and beams are casted monolithically. That means casted at the same time. So the option C is correct for this answer question. Next question is, the width of the flange of a T-beam which may be considered to act effectively with the rib of the rib depends upon. It is rib nothing but web we can call, right? Width of the beam, center to center distance of T beam, span of the T beam, all the above. The T beam effective width of the flange, effective width of the flange of a T beam, which may be considered for all. So answer is all the above. So let us summarize what are the things we have discussed today. We have discussed the classification of beams based on their shapes. Based on their shape, they are classified as rectangular as well as flanged beams. And the flanged beams are two types. Those are T beams and L beams. In T beams, we have classified based on the method of casting. There are two types, that is monolithic T beams and isolated T beams. And we have seen what are the Codal recommendation for monolithic and isolated T beams and L beams. Then we have discussed advantages of these flanged beams. And finally, we have solved some problems to calculate effective flange width of a T beams, and then we have seen some quiz questions. So that's all for today's class. Thank you.